Okay. So before I forget, just a couple of things. That Learn Smart assignment is due before we start class on Monday. So make sure you get on. Should take about 10 minutes. Get those easy points. Other than that, after class today, I'll post the next Connect homework. It'll be, we haven't worked through all the material yet, but if you want to get an early start on it, probably like the first half of the questions or so, you can probably start working on some of those. That due date will be pretty far off into the future. I just want to kind of get it up so you can kind of work on it as we go through material. Also, eventually we'll have the next Excel assignment, so kind of we'll have two things going at one time. So if you want to get a little bit of early work done on that, that'll be available. So add it in. If you're working off, like if you downloaded the file or the slides at the beginning of the week, I re-uploaded them. Would have been Wednesday after class, and it added some new stuff because I wasn't sure how quickly we'd go through material this week. So we've been talking about how we use that standard normal table last class, and that's when we're dealing with this standard normal distribution that has a mean of 0 and a variance of 1. But what happens if we're starting out with a variable that's not normally distributed with a mean 0 and a variance of 1, right? Most variables we look at, even if they're normally distributed, they're not going to have a mean of 0 and a variance of 1, so what do? So let's say we wanted the probability that this random variable x is in between these two values a and b. So what we're first going to do is take this normally distributed variable x that has some mean and some variance, and we're going to convert it into a standard normal distribution. Once we have a standard normal distribution, we can start to use that table to look up and find certain probabilities. So how do we turn things into a z-score? Well, we take whatever value we're interested in, so here that would be a. We subtract the mean of this x variable and divide by the standard deviation. Okay. How do I turn the value of b into a z-score? I subtract the mean, and I divide by the standard deviation. Once I have those two, I can start to think about what region I want. It's going to be the area in between these two z-scores that I've calculated. I can look up probabilities from the table, and then sometimes I have a final step, which is I have to, add or subtract or do something with those probabilities. Right? So I'll kind of give you a general idea of what this is going to look like. Oh, let's go to the dot cam here. So we're starting out. We've got some random variable x, and we know it's normally distributed. It has some mean and some variance, right? The mean's not 0. Let's say what we want, though, is the probability that I'm in between these two values. What I'm going to do is convert these into z-scores, which I know are standard normally distributed. Right? I'll kind of map these two values down to whatever z-score they become, right? So I don't know, maybe this is, 1.2 and 2.3. Right? I still want the area that's in between them. So what now I've kind of identified the region. I've turned them into z-scores, identified the region that I'm looking for. Well, that table is essentially the cumulative density function. So if I look up this z-score, the table will give me kind of this area right here. Right? And if I look up the z-score that is associated with that b value, it'll give me this area right here. So if I subtract this blue area from the green area, what I'm left with is what's in between or what I was originally looking for. Right? We kind of set these up in a general context when we were talking about continuous random variables earlier this week. But now we actually can look up what these areas are because all we have to do is look up those z-scores in the table. Okay? So that's the idea of what we're doing. We'll work with some actual numbers here in a second. And I'll leave this up here down in the corner. So those are kind of our steps. So let's say we put some numbers to this, right? So I got this normally distributed variable that has a mean of 5 and a variance of 25. What's the probability I see this x variable take on the values between 10 and 15? So it's going to be a pretty similar setup to what I had here, just kind of the general form. Let me get rid of this real quick. So what we're going to do is first think about, and you don't always have to draw this out. I think it kind of helps having a visual to go along with it. So we had a mean of 5 and a variance of 25, which the standard deviation would just be the square root of that, or the standard deviation ends up being also 5. Okay. I then wanted to know what's the probability I see it be between 10 and 15, right? So we actually have some values now. Okay. So the first step is I have to map this out or transform it to a standard normal distribution. Okay. If I turn the mean into a z-score, what should the mean always have a z-score of? If we think about the equation we're using for the z-score, it's that. So if I'm looking at the mean, I plug the mean in here for the x value I'm interested in, the mean minus the mean would always have a z-score of 0. And the area to the right of that z-score of 0 will always be what? Yeah, there's half to the left and half to the right of the mean. Our mean is 0. The area under the curve is 1, so half is to the left, half is to the right. Probably being above or below the mean is always 0.5. From there, I'm going to map out this value of 10 to its z-score and this value of 15 to its z-score. Right? So let's do this for the first one. I would have what? 10 minus that mean of 5 divided by my standard deviation up here, which was 5. I get this z-score of 1. Now let's think about what that means. Anytime we have a z-score, the interpretation is that's the number of standard deviations away from the mean, right? So this says that we should be 1 standard deviation away from the mean. Well, if we go back to the original data and think, how far away from 5 is 10? It's 5 away. What's the standard deviation? 5. So it is 1 standard deviation away from the mean. If I think about the value of 15, without even using this formula, how far away is 15 from 5? 10. How many standard deviations is that? Well, if the standard deviation is 5, that would be 2 standard deviations. Right? That's, when we calculate these z-scores, they always have that interpretation. And sure enough, if I plug 15 in to my z-score equation, I'll get that value of 2. Okay? Any questions up to this point? Okay with that? All right. So I can go to the table, look up that value of 1, and the table will tell me the area to the left of it. Right? I can also go to the table, look up that value of 2, and it will tell me the area to the left of that. Right? Once I have the smaller area, I'll subtract it from the larger area, and that would leave me with what's in between the two numbers. So how would we do that? Well, I'll go here. You got my table, that z table. I'm going to look up a z-score of 1. So I scroll down. Oh, you might have to reopen the file. Got way too many things open. There you go. I didn't drag and drop it over yet. Hold on. Sorry about that. I thought it would work. There we go. So I look for my z-score of 1. So I go down here, 1.00. That would be 1. So 0.8413. So I think about what I just found was the area to the left of 1, which was what? 0.8413. I then look up that z-score of 2, 2.00, 0.9772. So kind of this green area here, 0.9772. once I have those, oh, where did it just say I accidentally did something? Hopefully you guys are seeing the dot cam on Zoom. I thought I accidentally paused something. If you're not seeing the dot cam, let me know in the chat. So we've got these two areas. The original area I want to move is what's in between the z-score of 1 and 2, so I can subtract that smaller one from the larger one. Right, I get what, 0.1359, I think. Any questions on that process? And that last step might look different for different problems. We'll work through a few more, and we'll see that sometimes, you know, that transformation, it just depends on what area we're looking for, what we have to do at that step. Okay. We're good with that? Okay. So, I'll switch the screen over in class here. We'll wait for a second. There we go. So here's kind of everything we just did, right? We turned those two x values into z-scores. We then looked up the area to the left of each one of those z-scores. We then took the kind of red bricked area and subtracted it from the entire light blue area, right, where it crosses over, is where those two things will kind of cancel, and we'd be left with just what's in between the two, which was that 0.1359. Now, one thing to point out right away, and I've got a lot of things going on this graph, so we'll kind of remember from this one. If I was looking at these z-scores, so the area to the right of the mean is 0.5. So right away, I should have known I'm looking at an area that's smaller than 0.5, right? That's one thing that we didn't talk about, but using that idea that the area to the left and right of the mean is 0.5, we could have at least put a bounds on this probability that we knew it was going to be less than 0.5. And sure enough, once we end up calculating it, 0.3159. Okay. So let's look at a different, kind of data. So we're going to look at some rainfall data. Monday, we'll start with some Excel work with a normal distribution, and we'll be using I think I already have it up there on Canvas actually, but it's an Indiana weather data file. So I pulled some of these numbers from that. But we'll work it with it in Excel on Monday. So if we look at rainfall, it's pretty normally distributed, right? And if we have this data, we can easily find the mean or the average, right, using the average function. We can easily find the variance using that var.p function, or here we have sample data var.s. Okay. So I've got my mean and my variance. And if I look at the histogram, it ends up being normally distributed. So we've got the average kind of monthly inches of rainfall is normally distributed. Here's its mean, here's its variance. It varies by month, so we could calculate it by month as well. So some of the examples we do, I'll break this down to the month level. But if we look at kind of that histogram of monthly rainfall from the last 100+ years, it's really close to a normal distribution. I've got something kind of weird going on here, but for the most part, pretty normal distribution. Okay. So in 2012 in Indiana, and this was Indiana weather, not necessarily for the United States, just kind of looking at Indiana. So in 2012, there was this extreme drought. So you can kind of see there was they're putting out infographics about it to kind of let people know there's no rain. It was pretty hot, but the real kind of concern was that there was no rain. Right? It was this huge drought. Farmers took a big hit. We will just look at the timeline. It's kind of interesting. So we go back here. Notice here's January. Looks like February to kind of March. We see this uptick in kind of rainfall, and then it kind of goes back down in the winters again. You get to February and March, another uptick, falls again in the winter months. February, March, another uptick, falls in the winter months. We get to the next February and March. Not only do we not see this uptick in rainfall, it actually went lower. Right? So this is really what was causing that drought. Okay? So how likely was it that we saw some of these low rainfall amounts that we did? Well, over the entire kind of year, right, we saw average rainfall be 1.3 inches. Right? So what's the probability that we saw total rainfall be that low or anything lower than that? Right? And this might be something, if I'm planting, for agriculture, if I'm planting a certain type of crop and I know that I need at least 1.3 inches of rainfall, essentially what this is finding is If I see 1.3 or lower, I don't have enough to produce the product I need to produce, right? So if that probability is relatively high, I'll be concerned, right? So we've got this value we're interested in finding. We know the mean and the variance of this normally distributed variable. So let's just draw this out. And I'm gonna probably have to go back to remember what the exact values are because I didn't look at them long enough. I think it was what, 3.4, 2.57, okay? So we had what? This variable x was normally distributed. Was it 3.4 and 2.57, I believe? Maybe it's not 3. Is it 3.4 or 3.40. Okay, that's why. There's a second decimal. And I want to know what's the probability I see 1.3 or less. So what I'm going to do is map this out. First thing I have to do, transform this to a standard normally distributed variable, right? So what z-score will this end up being? Well, here's our z-score equation. So 1.3 minus that mean of 3.4. Now here, I have the variance of 2.57. So what I'm going to do here is just plug in the square root of 2.57, right? Because the square root of the variance, that represents my standard deviation. So once we do that, I can't remember exactly what, I think it's 1.8 maybe? No, negative 1.31 is what we'd get. Okay. So I now have, so negative 1.31. Right, that's my z-score. Once I look that value up in the table is the cumulative density, so it will tell me the area to the left. Here, I don't really have a fourth step. There's no transforming I have to do with those probabilities. So I'll look up 1.31, 1.31, so 0.9049. Right? Wait, what did I do wrong? I wanted negative 1.31, right? So I go back up here. Oh yeah, this makes a lot more sense. Negative 1.31, so let's come down, 0.0951. That makes a little more sense to me because, right, I know the mean is 0. I know the area to the left of 0 is 0.5, so the area to the left of negative 1.3 should have been something much smaller than 0.5. Sure enough, what was it, 0.0951, I think is what we found. Okay. Then I'm done. That's all I have to do on that one. That one's kind of easy. Okay. Any questions on anything, any step there? Or? Okay. Let's work through another example here. So this one's kind of interesting because this was, I think I took this from 2017, maybe in 2018 in September. We had a really exceptionally kind of dry September, right? Like no rainfall at all, 0.47 inches. So here's the average, the kind of mean and the variance. Right? Now, this is pretty similar to the previous problem, right? These are, pretty similar means and variances. So if 1.3 inches of rainfall was what? 1.3 standard deviations below the mean. How far away do we think 0.4 is going to be? Well, more than this, right? At least probably 2 standard deviations, if not more. So we'll go ahead. It's going to be the exact same setup. Kind of work through this one a little bit quicker. Nope. I've got stuff on the other side of these. I run out of paper. Oh, I think it's sandwiched in between here. Sorry, give me 1 second. There we go. So now what I'm thinking about is I have this monthly rainfall in September. See if I can get these. I think the variance was 2.37, and the mean was 3.25. I then wanted the probability, I saw 0.47 inches or anything lower. Right? This is the exact same setup as the one we had before. It's just we're working with different values, right? So I turn this into a standard normal distribution. I know the mean would have a z-score of 0, 0.47. I'll subtract the mean, divide by the standard deviation, right? Now, what I could have done here I'll rewrite the variance so we can see it at the same time. If I knew the variance, right, I could have calculated the standard deviation first. So I don't know if I do the square root of 2.37. I'm going to use Excel to cheat here. So square root of 2.37, 1.54 about. So I could have found this first, right? And then instead of the square root of 2.37 here, I could have just plugged in that 1.54. Right? If I do that, I end up getting negative 1.81. So it's a few more standard deviations away from that mean, right? I think the previous one we had was 1.31. Now it's the same setup. I look up negative 1.81, so 0.0351, 0.0351. So the probability that we saw, basically a ½ inch of rainfall or anything less than that, there's only about a 3% chance, right? Or 3.5% chance, probably a 0.0351. Just so you can kind of see this if you missed anything, filling in the back. But it was the same setup as the previous problem, just different numbers. Okay. Questions on that one before we keep moving? Okay. All right, maybe this one's a little bit harder. So, I have this broken down. We can do this by month, right? And different months have different means and different variances. Notice like June, much less variation in June temperatures than there is in February temperatures, quite a bit higher variance. So the average June temperature in Indiana usually has a mean of 70.75 and a variance of 6.3. Right? So what's the probability that the average June temperature is greater than 71.4? Well, first of all, I always kind of think if we calculate our standard deviation first, it's going to let us think about this a little bit better. So the square root of 6.3 is 2.51. Right? So if we're thinking about what we're looking at here, all right, a variance of 6.3, which is a standard deviation of, what did I say, 2.51. We're looking at this random variable x. It has a mean of 70.75, and we want to know what's the probability we see the temperature be 71.4 or anything greater. Right? That was what the problem kind of laid out for us. Now, if the standard deviation is 2.5, and I'm not even 1 away from the mean, how many standard deviations away from the mean am I? Way less than 1. I mean, not even a half here. Half of 2.5 would be 1.25. I'm not even 1.2. I'm not even half a standard deviation away. So right away, I know my z-score should be relatively low. Right? I also know that this area has to be less than what value? 0.5. Right? However, if I know that it's not very many standard deviations away, then I probably didn't really draw this perfectly to scale, because if this is less than a half a standard deviation away, the mean will have a z-score of 0. This z-score is going to be something that's, I don't know, let's say negative 0.3 or something, right? We haven't calculated it yet, but it's going to be something that's pretty close to 0, which means the area to the right is going to be pretty close to 0.5. But not quite, right? Not as large as 0.5. So if I was just looking at the answers here, just thinking about what we're doing, I'm probably going to guess A, right? A and D are the only ones that make sense. They're the only ones less than 0.5, right? But I think it's probably going to be a little bit closer to that value of 0.5 than I would be to 0, right? In order to kind of get these lower probabilities, we need to start seeing things that are multiple standard deviations away from the mean, or at least one standard deviation away from the mean. We're not even half a standard deviation. But we can actually go ahead and solve this. So this wasn't negative 0.3. It's going to be, well, take the value I'm interested in, 71.4, minus 70.75, so subtract the mean, and then divide by that standard deviation, 2.51. If I do that, oh, I said negative here, right? Sorry. I don't know what I was thinking. This can't be negative, right? As I'm looking at the right-hand side, I'm looking at something above the mean. So I meant like a theoretical could have been something like 0.3. Sorry. Oh, I'm going to have this in front of here. Sorry. So this couldn't have been negative 0.3. It has to be something that's small and positive. Wasn't thinking before I talked there. So if we go ahead, plug everything in, we get about 0.26, right? In fact, we really get 0.259. But why if I got, not 0.3, but 0.259, why is that a problem when I go to look at the table? The table only goes out to 2 decimals. So I'm going to have to round my z-scores to 2 decimals before I go to the table. So this we'll call 0.26. Now, when I look up in the table that value of 0.26, it's going to tell me the area to the left. I want the area to the right, so what do I need to do? Simply subtract whatever the area to the left is from 1, right? This is the area under the curve is 1, so essentially these two things are complements, right? So they should add up to 1. So I'll look up 0.26. Go to the positive side here, 0.26. So 0.6026, right? Which is the area to the left, so 0.6026. So I need to subtract that from 1, 0.3974. Okay. Any questions on that one? Okay. I want to make sure we do some inverse transformation ones. I got 20 minutes. I think we'll be all right. So let's say I have another kind of example that's really the same setup, right? I want to know what's the probability that I see something to be greater than, right? So I'm looking for the area to the right here. In 2017, there was an unseasonably warm February. The average daily temperature was like almost 43. And we have this mean of 29 or almost 29 and a variance of 26. So here's one where, unlike this example, like this one, there's the value we were looking for was very close to the mean. Well, here the value is pretty far away from the mean. But we also have a pretty high variance, right? If I look at the standard deviation here, it's going to be just over 5. Well, I'm still like, what, more than 10 away from the mean? So if the standard deviation is 5, I'm more than 2 standard deviations away. So I'm pretty far away. So right away, if I'm thinking about the same sort of setup, where I'm really just looking at different numbers here, right? This was like 28.89. This is whatever, the 42.85. And I said our variance was something like 26 point something, right? So we're still going to be looking for the same like area to the right. It's just that I now know this value is going to be more than 2 standard deviations away, right? If I take the square root of this, it's going to be approximately 5. It's going to be a little bit higher, but it's approximately 5. I'm more than 2 standard deviations away. So this area to the right of whatever z-score I find, it's going to start getting pretty close to 0, right? So if I'm just trying to take a guess on this one, just thinking about the principles behind what I'm doing, I'm probably going to guess B here. In fact, I know B has to be the correct answer, right? Because I'm looking at a value that is above the mean, right? I'm looking at a value, almost 43, that's above that mean. So right away, I know the area to the right of the mean is 0.5, so the area to the right of 43 has to be less than 0.5. If I look at those possible answers, there's only one of those that's less than 0.5. So it can't be C or D. A doesn't make any sense. My guess is A is the z-score that we end up calculating, right? So if I plug in that x value I'm interested in, the mean, and then here I've got my standard deviation, right, the square root of the variance, I get a 2.73 as my z-score. I then go, here's the second decimal, the 0.3, so 2.73, go up to the column, it's the 0.03, 0.9968. Well, 0.9968 is the area to the left. I wanted the area to the right, so we had to do that 1 minus, right? So I find kind of that area to the left of 2.73 at 0.9968. I subtract it from 1, and now I got the area to the right, or really the area that I was looking for originally. Okay? So, you know, the probability was as warm as it was in February of 2017, or warmer. There's actually like a 0.32% chance that it was that warm, or that it would be warmer this February than it was in that February. There's almost that's a very low probability. So you can start to do this with any month, anytime you see like an unseasonably warm or cold or dry or, month, you can look at this data and basically find how likely or unlikely it was that you saw temperatures be that high or low, or rainfall be that high or low. And we'll work with that, like I said, Monday we'll kind of work with that in Excel and see how we could do that very quickly. All right, any questions on this before we keep going? All right, so how do I want to think about it? Okay. We'll set this up with the formula first. So what we've been doing up to this point is taking some value of x and transforming it into a z-score so that the interpretation was this is the number of standard deviations away from the mean that this value was. Right? Once we know how many standard deviations away from the mean it is, we can start to find things like, well, what was the probability we saw something that far away from the mean? However, if we rearrange this, we can actually work in reverse, right? So if I just rearrange that z-score formula so that I'm solving for x, I get a slightly different equation, and I'll kind of show you how we can think about working backwards. Okay? So I'll write that again here in a second. What we were doing before is we would have some value for x, right? We would transform that into a z-score and then look up on the table the probability that we saw that z-score or anything lower. So we were starting off with a number here, working this way, where we calculate the z-score and then find the probability. However, if I know that I want to find, or sorry, I shouldn't say that I know. Let's say instead I'm looking for the x value that would give me a certain probability in this lower left tail. So maybe I know that I want 0.9 in that lower left tail. I would look up the z-score that has 0.9 to the left of it. The probability of seeing that z-score or less would be 0.9. Then from that z-score, I can work backwards using that inverse transformation function, right? Once I have the z-score, and I would know the original mean and the variance or the standard deviation of this original variable x, once I plug those in, then I can solve for that z-score. So it's kind of like we're working backwards. We're starting with the probability and finding the x value that would give us that area, or the probability associated with that x value. So everything's kind of going to be going in reverse here. So let's work with some actual numbers. So let's say I have this test or this exam, and the average is a 72 and the variance is a 64. Right? I think after I graded the exams, the average ended up actually being a little bit higher than this. That's why I decided not to kind of put a curve on it. The average is actually kind of where I usually see it. But this example, we have a little bit lower kind of an average. So 72 and 64. What's the lowest score that would still put someone in the top 10% of the distribution? So really what I'm looking for here is what score would give me 10% of the observations to the right and then 90% of the observations to the left. So we'll kind of work through this one. What I'm thinking about now is it's almost like I'm starting out and I say, okay, look, I want the z-score that would give me 0.9 to the left, right? Because that would be the kind of cutoff to where you would also see 10% of the test scores above it, right? Well, if I know the area that I want to the left of this z-score is 0.9, what I can do is go to my table. I no longer am going to be using the row and column heading to look up the z-score because I don't know the z-score yet. I know this green area. I know the cumulative density that I want, or that area in the left tail. So the area I wanted was 0.9. So I'm going to go search through here, find the thing closest to 0.9. Looks like it's going to be in between these two. Right? So the z-score that would give me exactly 0.9 in the tail would be somewhere between 1.28 and 1.29, right? Because I don't see exactly that probability of 0.9, but I know that it's going to be a z-score somewhere in between 1.28 and 1.29. Anytime we have an example like this, just take the higher of the two, right? So if I'm in between 1.28 and 1.29, I'm just going to use 1.29 for the calculation. Now, once we get to Excel, we'll see we don't have to worry about this. We can go out to whatever decimal point we want. But kind of doing this by hand, we're going to just use the higher and absolute value of the two, right? So 1.29 here. So 1.29 is the z-score that kind of gives me that desired area in the tail. So 1.29 is that z-score. I'm then going to work backwards to see what x value would be 1.29 standard deviations above the mean. Right? Well, the mean was 72. My variance was 64, so my standard deviation is 8. So I've got this inverse transformation function. I now have everything I need, right? I've got 72 plus 1.29 was the z-score times that standard deviation of 8. I think if I do this, I get what? 82 point something. All right, we'll see it in the slide in just a second, but it's 82 point something. So the test score that is the cutoff of the top 10% would be approximately 82. Any questions on that process before we kind of go back to the slides here? All right. So, all right, we found that z-score associated with seeing the area we wanted in the lower left tail, that 0.9. That's just a matter of plugging these values in. And like I said, we get approximately 82, 82.34. Okay. Now this makes sense, right? Because what test score, we go back with the original information, what test score would be the cutoff for the top 50%? Yeah, just the mean, right? Or 72. So we know that the cutoff for the top 10% has to be, something that's above the mean. So it's going to have a positive z-score, or that test score is going to have to actually be higher than the mean, right? And sure enough, whoops, it is, right? It's about 10 higher. Okay. So let's do the same sort of setup. But now we're looking for what's the score that would put me in the bottom 40%, right? What's that cutoff for the bottom 40%? Same mean, same test score, right? Same exam, 72 mean, 64 variance. Well, first of all, which of these don't make any sense at all if we're just thinking in the context of what we're looking for? we're looking for a test score that's the cutoff for the bottom 40%. I mean, we can't even, I don't even know how you see negative test scores on an exam, right? That doesn't make any sense. And 0.26, you know, if we saw a test score of 0.26 here without even doing the work, approximately what cutoff would that be for? The bottom, like 1%, right? It's gonna be like the lowest test score we could see. So we want 40% in that lower left tail. And we'll actually see we can rule one of these answers out as well. So let's just kind of set this one up. We'll start out, pretty similar setup. We'll think about our standard normal distribution. We want the z-score that gives us 0.4 in this lower left tail, right? Bottom 40% cutoff. Well, right away, I know this z-score that would give me 50% would be 0, right? That standard normal distribution mean. So I know this z-score is going to be negative, which also tells me that I'm going to be a certain number of standard deviations below the mean, and the original mean for that x variable was 72. So I know the test score for the bottom 40% should be less than 72. If I go back to those answers, the only one that meets that criteria here is D. I mean, these are less than 72, but we talked about why they don't make any sense, right? So from here, I need to look up that area of 0.4 on my table to get that z-score associated with that. So I'm going to hunt down the area of 0.4 here. So let's see. Looks like it's in between these two. So negative 2.5 and negative 0.25 and negative 0.26. I'll take the higher, that's absolute value, right? The one that's higher in absolute value. So negative 0.26. So I've got negative 0.26. We knew the variance was 64, or the standard deviation is 8. So now the x value, that would be the cutoff for the bottom 40%, is just, remember it's the mean plus the z-score times the standard deviation. So 72. I've got a negative 0.26 here, so minus 0.26 times that standard deviation of 8. And I think it's like 69.92 or something like that. Forget what the exact answer is now. Let's double check to see if I'm anywhere close. Yeah, 69.92. Okay. So just to kind of show that work one more time. You're still jotting things down. Any questions on that? Okay with that? Yeah.
So how do you know for the z-score, how do you know which side it's covering the area?
Which side is?
So the line, so how did you know for like the z-score
Mm-hmm.
that it covered the left side of that line?
So if I'm thinking about what's going to be the cutoff for the bottom 40%, I'm thinking about there's 40% of the test scores that are below me, right, or to the left. If I said something like, what's the lowest score that's going to be in the top 10%? Well, that means there's 10% of the test scores above me and 90% to the left. Now, it doesn't matter what the problem tells me. Like if it tells me that I'm looking for the cutoff for the top 10%, I don't want to look up 0.1 because if I just looked up 0.1, where did I put that? Here's the one that we did. It was 0.1. Did I not do it? I definitely drew one out for you with 0.9, didn't I? Oh, here it is. So even though I was told what's the cutoff for the top 10%, when I go to the table only has cumulative density probability, only gives me the area to the left, right? So I always need to figure out the area to the left first, right? Now, if it's directly given to me, like when I'm looking for the bottom 40%, so I had 0.4 to the left, but even if it says I want, what's the test score that gives me 10% of the test scores above it? Well, if there's 10% above it, or the probability of 0.1 of being above it, I automatically know the probability of being below it is 0.9 because the area under this curve is 1. Does that help?
Yeah.
Okay. All right. Any other questions? Okay. So that should take us through here. Here's all the kind of work we did as well. Kind of here we found the z-score, plugged everything in. Now you could plug it into the z-score equation and then solve for x. That's another way of doing it, but I don't know. It doesn't really save you any time or anything, but that is another way of thinking about it. Or unlike me, when I was working through this on the dot cam, I just found the standard deviation right away to make it easier. I knew that the square root of 64 was 8. You could just plug in the square root of the variance here and you end up with the same thing, right? Square root of 64. But I just think it's a little bit easier to first find the standard deviation and then work with that. I think that we'll do, like I said, we'll do Excel examples on Monday. So I think I'll leave you with, I found this a while ago. So if Hodgkin's was a normal distribution, you'd be 3 standard deviations above the mean. I always said you should change it to be that you're a z-score of 3. And then if they don't understand what that means, then you know that you can just walk away. They're not worth your time, right? So I'll leave you with that. I think pretty easy week after this exam. Just have that Learn Smart assignment that's due on Monday before we start. I'll get that next Connect assignment up as well so you can start working on that to get a little bit ahead. Other than that, we'll kind of pick up with this normal distribution on Monday. So have a fun and safe weekend.